There's a photograph that exists somewhere in NASA's archives that most people on this planet will never truly understand. It is not dramatic. It is not colorful. It is a dim, monochrome image of a dark planet lit only by the ghostly reflection of its own rings. And it was taken at 12:58 in the afternoon on September 14th, 2017, hours before the machine that captured it was deliberately sent to its death. No rescue, no return. A spacecraft that had traveled over 4 billion miles, survived 20 years in the cold void of space, and unlocked secrets that rewrote our understanding of the universe, pointed its camera one final time, captured one last frame, and then fell silently into the clouds of Saturn, burning like a dying star. What it left behind was not silence. It was a warning. Most people remember Cassini as a space mission, a probe, a scientific project that launched, did its job, and ended. They saw the headlines in 2017, scrolled past the images, maybe watched a short video of scientists crying in a control room in Pasadena, California, and then moved on with their lives. But what most people were never told, what the mainstream coverage consistently failed to communicate, is that what Cassini discovered in its final years, its final months, and specifically in those last terrifying dives it made between Saturn and its rings, did not just expand our knowledge of the solar system. It fundamentally changed the question we are asking about life in the universe, and that is a different thing entirely. Let's go back to the beginning, because the beginning of this story is as improbable as its ending. On October 15th of 1997, a spacecraft the size of a school bus was launched from Cape Canaveral. It carried the weight of 12 scientific instruments, 32.7 kilograms of plutonium for power, and the ambitions of over 5,000 scientists and engineers across 17 different nations. Its name was Cassini-Huygens, named after Giovanni Cassini, the 17th century astronomer who first observed the gap in Saturn's rings, and Christian Huygens, the Dutch mathematician who first correctly identified Saturn's rings for what they were in 1655. The mission was a joint production of NASA, the European Space Agency, and the Italian Space Agency. And it was going somewhere no controlled spacecraft had ever gone to stay. It was going to Saturn, and it would not be coming back for 13 years. Think about what that means. The engineers who built Cassini had to design a machine capable of surviving over 2 decades of operation in deep space. They had to account for radiation, gravitational forces, microimpacts, temperature extremes, ranging from scorching solar proximity during early flybys to the numbing cold of the outer solar system. They had to make it smart enough to operate autonomously when the signal delay between Earth and Saturn stretched to over an hour and a half. And then, because of the laws of orbital mechanics, they sent it on a 7-year journey that took it past Venus twice, past Earth, past Jupiter, swinging gravity assist after gravity assist like a stone skipped across a cosmic pond, before it finally arrived at Saturn on June 30th, 2004. The moment it fired its engines to slow down and slip into Saturn's orbit, the entire team at the Jet Propulsion Laboratory in Pasadena held their breath. They had been waiting 7 years for that moment, and it worked. But here's where it gets interesting. What they found when they arrived was nothing like what they expected. Within the first year of Cassini's arrival, something happened that nobody had predicted. The spacecraft swung close to a small, seemingly unremarkable moon called Enceladus, a body only about 313 miles wide, roughly the size of the state of Arizona. Scientists knew it was unusually bright and reflective, but they assumed it was geologically dead, a cold, passive, frozen world. What Cassini found instead was a moon that was essentially screaming into space. Enormous geysers were erupting from cracks near the South Pole, cracks that scientists nicknamed the tiger stripes, blasting jets of water vapor, ice particles, and gas hundreds of kilometers above the surface. Not water that had once existed and frozen long ago, water that was actively erupting. Liquid water, right now, in the outer solar system more than 886 million miles from the sun. Read that again. Liquid water, actively erupting from a moon of Saturn. The implications arrived slowly, the way truly seismic realizations tend to do. If there was water erupting, there had to be a source. If there was a source, there had to be heat. And if there was heat inside a moon that receives almost no solar radiation, something inside Enceladus was generating energy. The team adjusted Cassini's flight plan. They flew closer. They flew through the plumes. They pointed every instrument they had directly into those geysers and began to analyze exactly what was coming out. What they found over the following years constructed, piece by piece, one of the most astonishing portraits in the history of planetary science. Beneath that 16 to 19 mile thick shell of highly reflective ice, Enceladus harbors a global saltwater ocean. Not a small lake, not a buried reservoir, a global ocean. One that holds, according to estimates, roughly 1/10 as much water as the Indian Ocean here on Earth. The water is alkaline and salty, containing sodium chloride, ordinary table salt, which tells scientists that this ocean is in direct contact with a rocky seafloor. And at that seafloor, the evidence suggests There are hydrothermal vents, the same kind of hydrothermal vents that line the floor of Earth's oceans, the same environments that, down here on our planet, support entire ecosystems of life, tube worms, heat-resistant microbes, organisms that survive not on sunlight, but on chemical energy alone. In October 2015, Cassini made its deepest ever dive through the Enceladus plume, passing within 49 kilometers of the surface. Its ion and neutral mass spectrometer, an instrument that essentially sniffs gases the way a bloodhound traces a scent, detected something extraordinary. Molecular hydrogen, H2, pouring out of the plume in quantities too high to be explained by anything other than active hydrothermal chemistry happening at the seafloor right now. According to the research published in the journal Science in April 2017, the amount of hydrogen detected was high enough to support microbial organisms, if any exist there, in a process called methanogenesis, the same metabolic process used by certain microbes on Earth's ocean floors. The chemical energy was there, the water was there, the heat was there, the minerals were there. Every single ingredient required for life, as we understand it, existed on a moon of Saturn, in a place where the sun is a distant, faint star, no brighter than a very bright planet in our own night sky. Dr. Hunter Waite of the Southwest Research Institute, the lead author of that landmark paper, stated it carefully but unmistakably. We have not found evidence of the presence of microbial life in the ocean of Enceladus, but the discovery of hydrogen gas and the evidence for ongoing hydrothermal activity offer a tantalizing suggestion that habitable conditions could exist beneath the moon's icy crust. And what most people are not seeing is the weight of that sentence. Scientists do not use words like tantalizing carelessly. This was as close as a scientist operating within the constraints of peer-reviewed restraint can get to saying, this place could be alive. But Enceladus was only one revelation. Because while all of this was happening, Cassini was also building a completely different case about a completely different world. And that world was Titan. Titan is Saturn's largest moon, and it is unlike anything else in the solar system. It is the only moon with a dense atmosphere, denser, in fact, than Earth's, with atmospheric pressure at its surface about 1.5 times what you'd feel standing at sea level here. That atmosphere is thick with nitrogen and methane, and it produces weather. Real weather. Clouds form, rain falls, rivers carve channels, and lakes fill up, except none of it is water. The liquid on Titan is methane. And ethane, hydrocarbons that on Earth exist as natural gas, but on Titan's surface, where temperatures hover around negative 290 degrees Fahrenheit, pool into vast, calm lakes and seas near its north pole. The largest of these seas, Kraken Mare, is estimated to contain more liquid hydrocarbons than all of Earth's proven oil and gas reserves combined. Let that settle for a moment. In January 2005, the Huygens probe, which had been carried inside Cassini all the way from Earth, separated from its mothership and parachuted down through Titan's thick orange haze, transmitting data for over an hour as it descended. It touched down on what appeared to be a flat plain of rounded ice pebbles, shaped by liquid flow. It was the most distant landing ever achieved in the history of space exploration, more than 750 million miles from Earth. And what it found on the surface raised questions that scientists are still working to answer. Titan's chemistry, it turns out, is extraordinarily complex. Cassini's instruments detected negatively charged organic molecules, so-called anions, in Titan's upper atmosphere, species that were not expected to exist because they should react almost immediately with surrounding materials. What were they doing there? How were they surviving? And what were they becoming as they drifted down through the atmosphere and settled on the surface over millions of years? The real story here is one that goes beyond any single discovery. It is a story about what kind of universe we live in. Because for most of human history, the assumption, sometimes explicit, sometimes buried beneath scientific frameworks, was that life required very specific conditions. Conditions that only Earth seemed to satisfy. The right distance from the right kind of star, liquid water on the surface, a protective magnetic field, a stable climate. The more Cassini revealed, the more that assumption collapsed. Here was a moon, Enceladus, that met none of Earth's surface conditions, and yet appeared to carry every interior condition that life requires. Here was another moon, Titan, with chemistry so complex and an environment so rich in organic material that scientists had to invent new ways of even thinking about what life might look like under such different rules. We had searched the universe for planets like Earth, and the solar system turned around and told us we had been asking the wrong question. And then, in 2017, came the grand finale. By April of that year, Cassini had been orbiting Saturn for nearly 13 years. It had circled the planet 294 times. It had taken over 450,000 images. It had discovered 6 new named moons. It had sent back data that filled scientific journals for years, but its fuel was nearly gone, and the team at JPL faced a decision that was both practical and profound. If they lost control of Cassini, it might drift and eventually crash into Enceladus or Titan, the very worlds they had identified as potentially harboring life. Any microbes that had survived the 20-year journey clinging to the spacecraft could contaminate those moons and destroy the scientific integrity of any future search for native life. The decision was made deliberately and with full awareness of its weight. Cassini would be steered into Saturn's atmosphere and destroyed, intentionally, safely, sacrificially. But before it died, it would do something no spacecraft had ever done before. Beginning in April 2017, Cassini executed 22 successive dives through the 100-mile gap between Saturn and its innermost ring, a region so unexplored that scientists genuinely did not know whether the spacecraft would survive the first pass. Initial models had suggested the gap might be filled with dangerous dust and debris. What they found was that it was almost completely empty, surprisingly, unexpectedly, and mysteriously so. And from that intimate proximity to Saturn itself, Cassini gathered data that produced several more revelations that shook the scientific community. The first was about Saturn's rings. For centuries, since Galileo first observed Saturn's strange ears through his primitive telescope in 1610, the rings had been assumed to be as old as Saturn itself, roughly 4.5 billion years old, dating to the formation of the solar system. Cassini's final dives produced gravity measurements and dust analysis that demolished that assumption entirely. According to data published in the journal Science in January 2019, Saturn's rings are between 10 million and 100 million years old. From our perspective on Earth, that means the rings may have formed during the age of dinosaurs. Saturn itself is billions of years old, but those magnificent, iconic rings, the feature that makes Saturn the most visually stunning planet in the solar system, are geologically speaking brand new. They are a temporary accessory on a very ancient world. And here is what that implies. If you had built a telescope and pointed it at Saturn 200 million years ago, you would have seen a different planet, just a gas giant, no rings. And if you point a sufficiently advanced telescope at Saturn in another few hundred million years, the rings will be gone, raining down into the planet's atmosphere in a process scientists call ring rain, falling apart so gradually that by the time any future civilization notices it's happening, it will already be nearly complete. We are, in the entire span of cosmic time, the only civilization that has ever existed during the brief window when Saturn has its rings. Think about what that means. The second revelation from the grand finale concerned Saturn's interior. Cassini detected that Saturn's atmosphere rotates significantly faster than its deeper layers, something known from earlier observations. But the new measurements revealed that this differential rotation extends at least 5,600 miles deep into the planet. That is 3 times deeper than the equivalent phenomenon on Jupiter. And it represents roughly 15% of Saturn's total radius. The internal structure of Saturn, it turns out, is nothing like the simple models that textbooks had been illustrating for decades. There are complex layered dynamics deep inside that gas giant that we do not yet understand. And the precise length of a day on Saturn, something you might assume we'd have figured out long ago, remains uncertain because the planet's magnetic field tilt is so small, less than 0.06 degrees, that it provides no reliable rotational marker. The third and perhaps most haunting revelation came in Cassini's final measurements from its mass spectrometer, as it plunged into Saturn's atmosphere on the morning of September 15, 2017. Even as the spacecraft was being torn apart by friction and heat it was transmitting, the data it sent back in those last moments showed that material from Saturn's rings is actively falling into the planet's atmosphere. Not just water ice as expected, but complex organic compounds, ingredients more sophisticated than scientists had anticipated. The rings are feeding the planet, and the planet is pulling the rings apart. A slow, majestic, ongoing process of consumption that has been happening for millions of years and will continue until nothing of those rings remains. Scientists at JPL reported that contact was maintained for about 30 seconds longer than expected as Cassini made its final descent. The spacecraft fought to keep its antenna pointed at Earth for as long as its thrusters could manage, transmitting data even as Saturn's atmosphere began to tear it apart. When the torque became too great, the antenna lost lock with the deep space network. The signal died. And in that moment, a machine that had traveled more than 4 billion miles, that had crossed the solar system twice, that had revealed more about Saturn in 13 years than all previous observation in human history combined, became part of the planet it had spent its life studying. It became Saturn. The team in JPL's mission control did not cheer when the signal died. They cried, not because a machine was gone, but because they understood what had just happened. For 13 years, Cassini had been their link to a place most human beings will never go. It had been their eyes and their ears in a corner of the solar system so remote that the light from the sun arrives thin and cold. And now it was silent. The silence was not just technological, it was existential. But here is what you need to understand about silence. Cassini may have stopped transmitting, but it never stopped speaking. Because the data it collected, 635 gigabytes of scientific information gathered over those 20 years, is still being analyzed. Scientists are still publishing papers based on Cassini's measurements. New discoveries continue to emerge from its archives. In October 2025, researchers at the University of Washington published a new analysis of Cassini plume data from Enceladus, identifying fresh organic compounds in the ejected material, amino acid precursors, building blocks of the chemistry that, on Earth, led eventually to biology. The mission ended in 2017. The mission's discoveries did not. According to informed sources within the planetary science community, the Cassini dataset is expected to generate significant new scientific publications for at least another decade. The spacecraft is gone, but its legacy is a scientific library of the Saturn system, so comprehensive that researchers who were not even born when Cassini launched will spend their careers inside its data. That is not a metaphor. That is the operational reality of what Cassini left behind. And now the question the mission's findings have placed squarely in front of humanity is one that cannot be avoided, cannot be deferred, and cannot be answered without going back. The question is whether Enceladus, that small, icy, screaming moon, is alive. Not metaphorically, not poetically, biologically. The conditions are there. The chemistry is there. The energy source is there. Every ingredient that microbial life requires to exist and potentially thrive has been confirmed layer by layer, flyby by flyby, through 2 decades of measurement by one of the most sophisticated machines human civilization has ever built. What we have not done yet is go back with the right instruments and look directly inside. NASA has been developing a concept mission called Enceladus Orbilander, a spacecraft designed not just to fly through the plumes, but to orbit Enceladus, sample its ejected material with far greater precision, and potentially even land on its surface. The European Space Agency has its own proposed concepts, but these missions are still in the planning stages, still competing for funding, still subject to the political and budgetary realities that govern what any space agency is able to do in any given decade. The mission that could definitively answer the question of whether we are alone in the universe is conceptually designed and scientifically justified. All it needs is commitment. What most people are not seeing is the magnitude of that gap between what we know and what we refuse to prioritize finding out. We have found a world with a global saltwater ocean, active hydrothermal vents, molecular hydrogen, complex organic chemistry, and a direct delivery system that shoots its ocean contents into space where any passing spacecraft can analyze it without even needing to drill through ice. Enceladus is not hiding its ocean. It is launching it into space. It is the most accessible ocean world in the solar system. And we have not gone back since Cassini fell into Saturn's clouds in the autumn of 2017. Meanwhile, something even more unsettling sits in the background of all this. The data Cassini returned about Saturn's rings, their youth, their ongoing disintegration, the complex material raining down into Saturn's atmosphere, raises a question that nobody is loudly asking. If the rings are only tens of millions of years old, something created them. Something happened in the Saturn system within a geologically recent window that produced the most spectacular ring system in the solar system. The leading theory involves the gravitational disruption of a former moon, a moon that came too close to Saturn, was torn apart by tidal forces, and became the rings we see today. But if that is what happened, it means the Saturn system was dramatically different from what it is now, well within the time frame of complex life on Earth. Saturn's neighborhood was rearranged while dinosaurs walked this planet. And we are still working out the physics of what that rearrangement means for the broader history of the solar system's evolution. This is not a story about a spacecraft. This is a story about what we are. It is a story about a species that has been here long enough to build machines capable of answering the most profound question in the history of intelligent thought, and now has to decide whether we are brave enough, committed enough, and wise enough to actually use them. Cassini showed us that the universe does not reserve life for Earth alone. It showed us that the conditions for biology exist in places we would never have thought to look, on worlds we dismissed as frozen and dead and irrelevant, in a part of the solar system we called the outer darkness, and then it burned up in a gas giant's atmosphere, left us its entire archive, and went silent. The last image it ever took was dark, a monochrome view of Saturn's night side, lit only by the pale reflection of those temporary, dying, magnificent rings, pointing at the exact location where the spacecraft would crash hours later. A photograph of its own grave. And somewhere in that image, if you know what you're looking at, is not just a planet, it is a mirror pointing back at a small blue world, 894 million miles away, where a species with the intelligence to build Cassini and the wisdom to understand what it found still hasn't fully answered the question the mission made unavoidable. Are we alone? The answer may be orbiting Saturn right now, hidden beneath 16 miles of ice, circling in a dark, warm ancient ocean that no human eye has ever seen. Cassini found the door. we have not yet decided to open it. And the longer we wait, the more the question becomes not just scientific, but a statement about who we are, what we value, and whether we are serious about understanding the universe we inhabit. The machine is gone. The silence is complete. But somewhere in the data, in the chemistry, in the geysers still erupting into the cold, black sky above Enceladus right now as you read this, something may be waiting. Something that has been waiting for longer than our civilization has existed. Something that has no idea we are looking. And something that may, one day, be the most important discovery in the entire history of our species. The question is whether we go back before we forget what Cassini showed us, before the funding cycles turn elsewhere, before the urgency fades, before we convince ourselves, again, that the universe is empty and we are alone, and the silence means nothing. Because the last time we assumed that, a spacecraft flew through a plume of water erupting from an icy moon, and the universe proved us wrong.